Welcome everyone. This talk is Webauthn, don't do it wrong when doing it right. My name is Oscar. I work as a security researcher for Security Office. I focus mainly on authentication solutions. I'm based in South Korea, and sometimes I find and publish 0 days. That's me. All right, web authentication. Who here has heard about it? Quite a few. Who here has used it? All right. And who here has implemented it? All right. So just to recap, web authentication, it's a fairly new way of authenticating users to websites. It's designed to be phishing resistant and also passwordless. So instead of giving users a username and password that they can spread around on all different websites, you would have a fixed passkey that you can only use for a certain set of websites. So in order to log in, you just click a button, you either scan a QR code or you insert a USB stick. Simple as that. In order to understand how web authentication really works, we need to go back to school a bit. Asymmetric cryptography is what's laying the foundation for web authentication. In asymmetric cryptography, you have basically two things. You have a private key and you also have a public key. The private key is something that you should keep secret at all times. And the public key is something you can just hand out to everyone, your friends, your system, whatever. Using your private key, you can then sign stuff in order to prove that you are you. So in this case, we have a user, let's call her Alice. She signs a message saying, hey, I'm Alice. And then Bob and another system can just verify this message by using Alice's public key. All right. So how does this work with web authentication? Web authentication has two scenarios. We have registration and authentication. When we do registration, we generate a key pair. We scope it to a certain set of websites, saying that you can only use this passkey for this website. And then you upload your public key. For authentication, you sign a challenge that you get from the website. You send it back, and then you let the server verify it. So in practice, this looks something like this. You have a user agent, i.e. a browser, and the user says, hey, I want to log into your service. The server then says, yeah, okay, right, here's a challenge. The browser then communicates with the authenticator, saying, okay, here's a challenge, here's the credential ID, here's the relying party ID, and here's the origin. It does this by using the Web Authentication API. The authenticator will then communicate with the user, saying, do you really want to log into this relying party? Is this the website that you're on? If the user then agrees, it will either input a PIN, it could use a fingerprint, or even use facial recognition in order to authenticate to the authenticator. Now, the authenticator will sign the challenge. It will forward the challenge then to the browser. The browser will send it to the server, and then the server can just verify it using the authenticator's public key. All right. So how does it really work? Web authentication consists really of three things. You have the relying party server, you have the browser or the user agent, and then you have the authenticator. So the relying party server, as we just saw, is responsible for issuing this challenge, communicating it to the browser, and then the browser will use the Web Authentication API in order to communicate with the authenticator. The authenticator will then prompt the user, hey, do you want to log in, as we just saw. In that case, the browser will then just forward back the signature for the challenge. Note here that the browser never sees any of the private key data. It only sees the signed challenge. So it never touches any of the sensitive data. As an example, this is how you would use the Web Authentication API. It's really simple. It's 17 lines of code. Most modern browsers today support this. An example of a request looks like this. We have a challenge. We have an RP ID named example.com. We also have a credential ID, and we also tell the authenticator how we should do the user verification. This is how an example response looks like. This is what the browser sees. This is what the browser will then communicate back to the relying party server. As you can see here, we have a signature. We also have a user handle that will tell the website what kind of display it should use for the end user. All right. I talked a little bit about it being phishing resistant. So how does that really work? Why can't I just put a QR code on website A saying, hey, I'm website B? Let's look at how Chromium does it. In order to prompt the user for a web authentication request, it will first call the method validate domain and relying party ID. Inside this method, it makes another call to origin is allowed to claim relying party ID. All right. If we go into that method, we see that it checks if the caller origin is exactly the same as the relying party ID. If that's the case, it will prompt the user for the web authentication prompt. But it also makes another request or another call to domain is. It's a lot of code to look at, but at the end of this, it checks that the caller origin is actually a subdomain of the relying party ID. All right. What even is a relying party ID? Which is this caller origin? What is this? The relying party identifier is what is RPID. That's what binds your passkey to a certain service. So for instance, if you want to log into Gmail, you would just use one passkey. You wouldn't want to use one passkey for Gmail, one for Google Calendar, etc. You would want to scope that into one passkey, right? All right. If we look at the standard, it clearly says that by default, the RPID for a web authentication operation is set to the caller's origin effective domain. This default may be overridden by the caller as long as the caller specified RPID is a registrable domain suffix or is equal to the caller's origin's effective domain. That's basically what we saw for the Chromium source, right? So this means that www.example.com would be able to claim example.com as their RPID. All right. But what about marketing.example.com? What about mail.example or vulnerablecms.example.com? You guessed it. They can all also claim example.com as their RPID. And we know that organizations use this kind of subdomains for their services. But you might not want your user to be able to log into vulnerable.cms.example.com for your service. It should only be login.yourservice, or it should just be yourservice.com. So how do we fix this? If we look at standard, it gives a pretty straight answer. It gives you 16 validations that you need to do in order to verify the origin and in order to verify an authentication assertion. Once you have implemented those 16, you can do 6 more because it's actually 22 steps. If you paid attention, there's one particular step that is important for our case, and that is step number 13. It says, verify that the value of client data origin matches relying party's origin. Seems pretty straightforward, right? Let's read it again. Client data origin matches the relying party's origin. There's no ambiguity there, right? What about this word? Is it supposed to be a string match? Is it supposed to be an exactly match of the effective domain? Or is it supposed to be like what Chromium did, just a subdomain? So let's go back and look at what the standard says. First of all, you might notice there's no mentioning here about relying party origin. So what should it be? I don't know. Doesn't say anything. It also says, like I just said before, that this default may be overridden by the caller as long as the caller specified RPID value is a registrable domain suffix or is equal to the caller's origin's effective domain. Okay, it still doesn't seem pretty clear to me. So what should we do in this case? Luckily, the companies that actually write the standard, they also write libraries, which means that we can look at more libraries. It's going to be more code, and it's going to be fun. Some libraries, they just skip step 13. There's no check whatsoever about the origin. Some libraries, well, at least they try. In this case, apparently evil example.com is equal to example.com. And some, they go exactly with Chromium's approach, just checking if it's a valid subdomain. But some libraries, they actually do it correctly. So what they will give you is you need to specify either a list or just one origin that you are expecting to see when you validate a web authentication assertion. Funny thing is, most of the examples we saw, they're actually written by the companies that wrote the standard. So it seems like they also don't really know what to do. So how can we exploit this? It's demo time. All right. So here we have an ordinary user to the right. We have an attacker to the left, marked here by the red browser. The normal user will register using a web authentication request. Here it's using hello, Windows Hello. Once that's done, the user can then log in. It gets prompted by the Windows Hello. Log in as victim. All right. Now, the attacker, as we can see, is not logged in at the moment. However, the attacker has identified a vulnerability on a different subdomain. So in this case, news. This is maybe not a subdomain where you want to let your users log in. You should only be able to log in from the main domain. So using this vulnerability, it's a cross-site scripting, we can launch an attack towards the victim. So in this case, the attacker then sends the victim a URL. As soon as the victim clicks it, it gets prompted to input the PIN for the web authentication. Note that this is just happening in their web browser, nothing else. The victim then logs in, or does it? The attacker was able to steal the web authentication response, forward it directly to the web authentication server, and then log himself in. So that's a way of stealing web authentication responses. All right. Let's go back. How can we fix this? In the new standard, it's still a working draft. It's not released yet. They have added some stuff. It's no other than 3 more stuff that you should do when you verify this. We have a clarification regarding how you would verify the origin. So now the origin needs to be really expected by the relying party server. There's also a whole new section about validating the origin of a credential. So you should do an exact string match, or you should have a list of expected origins. All right, so we talked about browsers, we talked about relying party servers. Is there anything else? There is more. We still have the authenticators. So since Android 14, there is a new API called Credential Provider Service. With this API, you're able to make yourself your own authenticator. So this is something that password managers would use in order to support passkeys. So 1Password, LastPass, etc. They all use this API. It's fairly easy to implement. All you need to do is register yourself as a service in your Android manifest. You configure yourself to support passkeys. Once you've done that, you're able to handle passkeys within your own application. So how does this work? Let's say that we have a browser on your mobile phone, in this case Chrome, and you want to log in using web authentication. Chrome will talk to Credential Manager as part of Android OS. It will send a GET credential request. It will contain the web authentication request that we saw earlier. It will also contain the origin of the website that where you want to log in. Credential Manager then will query all the credential provider services that you have installed and enabled. It does this by using a begin get credential request, and this will contain calling app info saying, hey, this was Chrome calling you, not this malicious app. It will also contain the web authentication request. If you have a credential ID mapped to this credential, your credential provider service will respond by sending a begin get credential request response. It will contain credential entries. Each of these entries will have a pending intent, and this is very important to keep in mind. At this point then, Credential Manager will prompt the user saying, hey, I found these credentials, which one do you want to use? If the user then picks one, it will then use the same pending intent, send it back to the credential provider activity, which is now a separate activity than the service. This is also why the pending intent is used. The credential provider activity then is responsible for actually verifying that the user is who it says he is, either has the PIN or the fingerprint or facial recognition. If that's the case, then the credential provider activity will send a response. It will have the response data of a web authentication response, as we just saw. It will then, Credential Manager will then send that back to Chrome, who can then send it back to the web authentication server and then authenticate the user. And you might say, why can't I just use a malicious app to make this request instead of Chrome? What's the difference, right? There's something called privileged app. There's something called allowed apps. For privileged apps, such as browsers, they need to be able to set different origins. After all, that's what you use in order to go to different websites. To do this, they need a special permission. It's called Credential Manager Set Origin. This is a normal permission, so anyone can actually ask for it. However, all the signing info for this privileged app will be published by Google at this special URL. So you, as your credential provider, you should query this endpoint and then look if the calling app info is the same as what's published on this endpoint. If it's not a privileged app. For the allowed apps, let's say that you have a native app that you want to use in order to call the rpidexample.com. In this case, it works pretty much the same as universal links. So you need to publish the app's signing info on the digital asset link. After that, you can use the app just as the browser to log in and to query the credential manager. So for malicious apps, it will not have the correct calling app info. As we can see here, it still says com malicious package. It will not be published by Google at this special URL, and it will not be in the victim's digital asset links. All right. I mentioned pending intents before and why it was important. Intents in Android, they're used for communication between apps and activities, which means that you cannot reach non-exported activities in external apps. If you have an application that does not expect to receive an intent from another app and the activity is not exported, you cannot call it. However, with pending intents, that's completely different. Pending intents is used to pass on privileges to another app. So in this case, application A can just send a pending intent to application B saying, hey, you can come back to me and use this pending intent later. Application B can then act as application A, which means application B can call non-exported activities in external apps. So what if we have a credential provider activity that accidentally has exported itself? So here we have an example of that. We have a get passkey activity. It has the Android attribute exported set to true. Fun fact, this is actually Android's official sample for how to implement credential providers. So using this, we can form an attack. Our attack plan is basically, since we can call this activity as is, we can spoof a privileged app's calling info. We can forge our own get credential requests. And then, as I just said, since it's just exported, we can just call it as is. And you have to remember, intents are just bundled data, so you can put anything in there. Let's start by spoofing Chrome in this case. Calling Chrome, getting the package signing info, putting that into my intent. I'm then forging a normal web authentication request, putting that in my intent as well. And then we just fire it off. Let's take a look at how this would look in reality. So here we have a user trying to log in to the same demo site as we saw before. Oh, sorry. Could be good so you actually see something. How about now? Yes. All right. We have a user trying to log into the demo site as we saw before. In this case, it's on a phone, logging in using my credential provider this time, not the malicious one. Signing in works like that. We can see here that the authenticator will ask the user, are you sure that you want Chrome to be able to log in to webauthn.se? If that's the case, the user will then push authenticate. When this is done, the user is once again logged in. It then launches the malicious app. The malicious app will spoof a get credential request, send that intent to the credential provider. You saw it flashing by real quick there. I can do it again. So not only were we able to bypass and call the authenticator directly, we also did not get the prompt saying, hey, are you really sure that you want to authenticate using Google and to this origin? As we can see here, the malicious app was able to get the web authentication response. And using this, it can then communicate directly with the service to get logged in. This would, of course, be done in the background. This is just for demo purposes that you can see it. All right. So when you implement web authentication, make sure that you clearly define your origins. Don't be surprised if it comes a web authentication response from an origin that you've never seen before. Make sure that you really know what you're doing. If you're a user of web authentication, please use well-reviewed and also tested authenticators, preferably someone that does not export the most important activity in their manifest. If you're implementing it, please conduct code reviews if you have the possibility for it. And since this is a pretty new standard, things will change, so make sure to keep up with what's new. And as always, perform security assessments of your services. Thank you.